Now, okay, in the last hour we talked about how to build a multiple regression model, which is we use a series of X to predict Y, right? And in that case, we actually can, what do you call it? And we learn how to split the data for training and testing, right? And then we explain why we want to do that, right? Why in the current data science we want to reserve some data for testing the accuracy of the model, okay? So we only use the training data to build a model, and we explain how to see how to assess the relationship between all of the X toward Y, right? Toward temperature, all of this X toward temperature, and that can actually be seen in this p-value, right? Okay. Again, if the p-value is very low, it means that we have a high confidence that there is a relationship between X and Y. And if the p-value is kind of high, right? For example, this p-value is very high, and we will say that its relationship with Y is not significant, right? We don't have the confidence that they have okay. So basically, this is the estimation value, and this is the associated expected value, and this is the associated standard error, right? And with that, we can actually have an idea about the relationship between X and Y. Okay. So the one thing that I want to emphasize is you don't just look into this the estimation. You need to take a look at the you actually need to take a look at the coefficient standard error, right? We explain that later, but before that, let's take a look at the model accuracy measurement, okay? Which is a very, very important thing that I want to explain here, right? Okay, so when we talk about model accuracy, we are basically talking about the difference between Y and the estimation of Y, right? Isn't it? Right? Okay. So there's a thing called variance, okay? We first of all, to calculate model accuracy, first of all, we want to evaluate the variance of Y itself, okay? And it's called sum of square total, okay? As you can see that in this equation, this is Y and this is the average of Y, okay? So there are a lot of Y, right? We in this case we have like 308 Y. This is the Y bar, is the average, okay, of that. And you can see that now. Suppose that we are going to I think it is here, okay, here. Okay, the variance in Y is calculated this way, right? Why we want to estimate the variance in Y? Because the reason that we want to use model to estimate Y is because Y is jumping around, right? It's jumping up and down along its average, right? This pink bar is actually the average of Y, right? So if we do not use X, we can still estimate Y by its average, right? So the variance of y is how the value of y itself is deviated from its own average. Okay, the variance of y actually implies the how each individual y value is deviated from its average. Okay, this is y, right, and this is the average, right? So we call sum of square total is sum of square, right? It's the sum. This is the summation, right? Sum of square. Okay, so how y is deviated? If the y is deviated from its average, very far away from its average, if y is jumping around, usually it often jump very far around its average, then its variance is very high, right? So it means that it's very difficult to predict y, right? If y is a very large variance, then it's difficult to predict y, right? And the reason that we want to use a model to predict y, this is different. You can see the difference between these two equations. The only difference is here, right? This is the average of y, which is the pink line, right? Horizontal pink line is the average of y, okay? So, and this is actually the y estimation, y hat, right? So the y hat, as I told you, it basically lies along this linear line, right? Isn't it, right? So if we estimate y with this line, it would actually, the error is actually smaller, right? Isn't it, right? So so the error from y to its average and the error of y toward the model estimation are different, right? Okay, so when we are estimating the accuracy of y, we usually use this equation. Okay, first of all, we calculate the variance of y toward its average. Okay, and then we calculate the variance of y along the estimated value, which is the residual after regression, right? Okay, I say it again, right? First of all, we calculate the variance of y itself, okay, which is the variance of y against its average, okay? And then we calculate the variance of y against the estimation value, okay? And if the model is good, then this sum of square error is like very low, right? It's very low. Ideally, if they have no error at all, right, then you can see that this will become zero, right? And if the model is bad, right, if the model is pretty bad, then this sum of squares is actually very large, you know, right? So so this R-square value is a value that that range from 0 to 1, right? The largest value is 1, the smallest value is 0, and it actually implies the fraction of variance expanded by the model. Okay, so for example, if R square is like 60%, 0.6, okay, it means that the model can reduce the error by 60%. Okay, in terms of variance, it expands the 60% of y's variance if the R square equal to 0.6. Okay, If the R square is equal to 0.4, then it implies that the model can only reduce the variance, okay, of y, reduce the error of y by 40%. Okay? So R squared, it means the amount of variance of y, the fraction of y's variance that explained by the model. So if R squared is very high, it means that it means that the model is very good, right? Because the residual will be very small, isn't it, right? And the R squared would be very close to 1, okay? And if the R squared is close to 0, it means that the model is not so good, right? It only explains a small portion of variance of y itself, okay? So R squared is actually a very often used measurement of model accuracy, okay? The good thing is that it's always stay within 0 and 1, okay? And it also have a implication, okay? It means that it actually implies the fraction of variance of y itself that can be it can be reduced by the model, okay? So say if it's 0.8, it means that 80% of y's variance can be explained by this model, okay? You get the point? Okay. So as I can see, I already written here and actually you can see the R square value in the you can see the R square value in here. You can see that, right? So this model is like pretty good, right? Okay, it explains like 75% of y's variance. Okay, right? You get the point? Okay, so that's how this is one way that we can estimate the accuracy, the goodness of fit, in another word, okay, of a model, of a linear regression model, okay. And the other way to measure the error is actually use this SSE, and we can actually, from this SSE, it's actually the same as this SSE, right? So with this SSE, we can actually also calculate the, this is the way to calculate IMSE and also MAE. Both of them actually imply the average error. We know that there will be an error, but every individual point the error are different, right? So another way to measure the accuracy of a model is to calculate its average error, and there are two different ways of estimating the average error. And this one is pretty straightforward, right? It's just the absolute value of the residual divided by n, right? Because we are talking about average error, right? And this is another way to do it. Well, in the statistic, sometimes you will prefer to use this one, but we do not have time to explain that why they do it this way. But basically, it will be easier when you want to do further statistical inference. Then you will use this one, right? And if you care about the actual or average error, then you can use this MAE. Okay. However, we can say that if you have a larger average error, then you will have a lower R squared, right? So R squared is the higher the better, and the IMSE and MAE the lower is better. Okay. And let's take a look at how it works. Okay, let's do some calculation, right? Okay, so first of all, we can measure the accuracy in the training data, right? Okay, so if we want to do the prediction of the training data, we don't need to give it any new data set, right? The data set is already in the model. Okay, within the model, it already has the training data set, right? So if you simply call predict with the model, then you will return the estimate value of training data. Okay, but this prediction is different from the actual value, right? Okay, this is the actual value, right? Actual value is in this column, right? So we take the difference between the predict value and the actual value and square it and sum, right? This is the sum of square error, right? Isn't it? This is the error, isn't it? Right? And we square it and we sum it. It's the sum of square. Actually, it's exactly this SSE, right? And then we can actually calculate the SST, right? And right now, this is the actual value of CS. You can see that this is the actual value of Y, and this is the average of Y, right? So, and Y is TR 10, isn't it? Right? So this is the average of Y, which is Y bar, and this is Y itself. And again, it need to be square and then sum. And this is the variance of Y itself, right? Okay? So, and again, use this equation. We can estimate the R square, and then use this thing, we can estimate the IMSE, right? Okay. If you want to estimate MAE, you can also estimate MAE. But right now, remember that all of these things is actually the accuracy of the model on the training data set itself. And as I told you in the beginning of this hour, that recently in data science, we don't like to do that, right? When we want to measure the accuracy of a model, we want to measure the accuracy by the data that has not used during training. Okay? So the model is good only when it can predict the value that it had not seen before, right? So that's the reason that we predict some data for testing, right? And the calculation is basically all the same, right? As you can see that the calculation is basically everything is the same, except that right now we are using TS instead of TR, right? This is the first important thing, okay? And the second important thing is that we need to use TS to do the prediction, right? Okay? And the rates are all the same, right? But you need to be careful that this when we are calculating the average of Y in testing data set, we are still using the training data set as mean, right? I do not have the time to explain why we want to do that, right? But be careful, because here is TR instead of TS, okay? So this is TS, but here is TR, right? There is a reason to do that. When you learn the machine learning type of course, if you explain how or why we want to do that, okay? So this R squared is actually can be lower than 0, actually, because we are using TR instead of TS, okay? And the rest are all the same. So if you compare the two things, right, you can see that the, for example, if you want to compare the R squared, in training data, the R squared is 0.75, and in testing, we can only see the R squared as 0.62, right? Okay, it means that the model is performing well on training data, better than the testing data, right? Okay, so, and if you look at the average error, right, RMSE, right? So again the average the average error in the testing data set is higher than training, right? So it also implies that the model is performed better in the training data set than in the testing data set, which is all usually the case, right? Okay, and basically, if you have the chance to learn machine learning, there are many ways to try to make the data set, make the training and testing data set result pretty much the same, right? The reason that we have so much difference here in this model, the major reason here is that we have a very small data set, right? Right now we only have like, here we only have like 306 data point, right? We only have like, we're training only with 280 point, right? Okay, and we're testing only by 24, right? So in case of Tafang, when your data frame is like customer, right? We have about 30,000 customers, right? When you have a large data set, then you will see that the difference between training and testing will be kind of like lower than this little data. Okay, so this is to show you that the importance of reserving data for testing, okay, and how to calculate the accuracy of how to assess the accuracy of model by testing data set. Okay. So usually in business case, in business analytics, we will be asked to present your accuracy in testing instead of in training. Okay, if you are reading paper using data science method, then you will be asked to present your accuracy in testing instead of in the training. Okay. In a traditional statistic used to like present this value, but modern data science we will use this measurement in the testing data. Okay. Now there are some discussion, right? In the aspects of business, which of the following do you care most? Okay? Do you care about the coefficient, the p-value, the significant, and anything else? Okay. So which one do you care most? Right? Well, it's my own opinion. The first thing I care is the coefficient itself, right? Because it implies the relationship. Okay? It implies the marginal effect of x toward y, right? Isn't it? Right? So in the sense of business, I want to know that for every million I spend on an advertisement, how much my revenue would increase, right? That is the marginal effect of x toward y, right? And that is actually the B1 value, the coefficient itself, right? But the coefficient is not, the coefficient estimation is only, as I told you, that this is only the expected value. In addition to expected value, we also need to consider its standard error, right? As I told you that uncertainty is always there, right? It's just, with this expected value, it comes with a standard error, right? So in this chart, I try to, don't worry about the code, right? I'll just take a look at this chart. See, this is B3 associated to CO2, B4, it's not significant. B5 is barely significant, and B7 is like very significant, right? B4 is not significant because, like, as you can see, that its expected value is very close to 0, isn't it? Right? Obviously, it's 95% confidence level with here, right? So it's not significant because its estimation value, estimation value is very close to 0, right? Okay. But there are a few interesting things that we can observe here, right? For example, this B7 is actually very significant, right? It's the most significant actually because it has 3 stars, right? Okay. So here I have a set of which gas has the largest effect on the temperature. Is this significant? Can you see from here? The expected value is the expected value is here, right? And the expected value here, expected value here. So this 4 coefficient, okay, which one has the largest expected value? Which one? This one is the smallest. So which one is largest? Is it this one or this one? It is lower than 0.1, right? But this is already larger than 0.1, right? So the largest coefficient out of the 4 is what? Is B5, right? Isn't it? Right? But Z5 is barely significant, right? The most significant one is actually this one, right? B5 has the largest coefficient, but it is not significant. Why? As you can see that B5 has a p-value of 5. B5 is what? B5 is CF12. As you can see that, where does it go? Okay, it should be, yeah, I think it should be this one, right? NO2. Okay, so it's barely significant because its p-value is actually larger than 0.5. Okay, so it's not significant, but its coefficient is the largest. I mean, absolutely, in the absolute value. Okay, why? Why it has the largest coefficient and it's not, it's barely significant? Why is that? As I told you that all of these coefficients, they have an expected value, right? And it also has what? In the summary, it estimates not only the expected value, but also what? Standard error, right? Okay. The reason that the largest effect is not significant is because that it associated with a very large standard error, right? It means that the largest standard error implies that the model, when the method estimates this coefficient, it do not have a good confidence, right? Large standard error means large uncertainty, right? So it is not sure about this value, okay? So it actually was estimated with a larger standard error, right? And because its standard error is large, right? So as you can see that its right tail is actually, right, cover 0, right? That's why it is barely significant, okay? And although its expected value of this yellow line is like is quite small, right? But because it has a short coefficient, has a very small standard error, then as you can see that it's very, very significant. So that's one thing that I would like to remind you that when you look into the model summary, when you assess the relationship between X and Y, don't just look at the estimation value, right? You need to also take a look at the standard error. Or the other way is to take a look at the p-value, right? Okay? So that's the one thing that I would like to illustrate in this chart. Okay. Oh, the advantage that we learn statistics in R is that you can always make a chart very easily, right? So you can see the concept of expected value and see the importance of standard error as well. Okay. So there are some discussion here. This question I already discussed, right? Which gas has the most significant? Does it bear the largest effect? Can you answer this question? Because it would be your homework assignment, right? So the most significant is this one, right? And does it has the largest estimating effect? Okay, this is the second question. And so can you explain the inconsistency, right? In these two things, we see that the gas that had the largest estimated effect is very significant, and the most significant gas does not bear the largest effect. So there are some inconsistency, right? Why is that consistency? Actually, I already explained to you, right? Yeah, because the standard error, right? Which implies that the method, when the method estimates the expected value, it sometimes has uncertainty there, right? The larger the standard error, a large standard error implies that the method is just not quite sure about the accuracy of that coefficient, so you need to be careful, okay? Another thing that we need to explain is so-called collinearity, right? When you have a lot of x, when you use a lot of x to estimate y, right? There will be a problem, right? Because some of this x has very high correlation. If we visualize this, there's a way to visualize this. This is called correlation matrix, right? We done that before, right? So as you can see that this predicting variable among themselves, some of them has a very high correlation for NO2 and CO2. The coefficient is as high as 0.98, which means that their value are very has very strong correlation within themselves, right? And when they have such a strong correlation, it would affect the accuracy of the coefficient, right? See, it means that within the data, when CO2 is high, NO2 is also high. When CO2 is low, NO2 is also always low, right? I mean, within the data, when you see a correlation of this high, right? It means that I can almost predict NO2 by CO2, right? Isn't it? Right? Correlation is so high. When correlation is so high, then the method is no longer be able to distinguish the effect of CO2 and NO2. Okay? Well, both of this case, they if within the data they have a very high correlation, it will cause a collinearity problem, right? It's the jargon of statistics, right? And with this high correlation, usually it will affect the accuracy of the coefficient. Okay, so sometimes we need to adjust our model to avoid this collinearity. Then in R, it's actually quite easy to do that, right? We can simply build a model. We can actually look at this correlation table, right? And manually remove the high correlated regressor, the high correlated X, help to avoid collinearity, right? So if you remove the high correlated X, then you will have a better confidence, right? And usually we will associate it with a better p-value, right? For your model, right? As you can see that if we use just 4x to predict temperature, okay, p-value is very high, okay, and we will have a better confidence on this coefficient, okay. However, when you have a less x, then the model accuracy dropped from 0.75 to 0.72. You see that? So for linear regression model, okay, if you have more predictive variable, you will always have a larger R square, which means that if your purpose is only to predict Y, right? You do not care about the accuracy of this coefficient. If your purpose is to predict Y, then you should put all of the variable into that model. That is not a problem. Right? But that would cause a estimation of coefficient not reliable, right? If among them they have high coefficient, okay? So if you also care about the accuracy of this coefficient, then you can actually like remove the high correlation X, okay, from the model, right? That's one way to do that, okay? And the second way to do it is like you simply put the this M1, right, which is the A coefficient model, and then call a step built-in function, and the R will select the a new model for you, and as you can see that if you call the step, it actually 1, 2, 3, 4, 5, 6, 7. You would only remove one variable out of the model, right? Okay. Actually, the last thing that I want to emphasize to wrap up this linear regression is that the linear regression is the simplest and also the most difficult method to use, right? Okay. What we call is simple. It's because that it only uses right, a very simple mathematical equation, right? If you look into the decision tree or like the other type of model, you will see that the mathematical equations like is kind of very. It would take like, if you are using a decision model, you may need several pages, right, to express it mathematically, right? But with linear regression model, that it uses a very simple mathematical form to do the estimation, okay? But the difficulty is that if you want to, and actually because of its simplicity, it is less precise, okay? If you want to have a very precise model, you better choose the machine learning model or like artificial intelligence model, right? Okay. Accuracy would be better. Actually, not much better. Maybe better than 5% also, something like that, right? So if you care about the accuracy, you actually can choose to use the machine learning model. But whatsoever, it's less precise, but it's yet most useful. The reason I say that is because that it is the only model that show you the marginal effect from X to Y. Okay? And that sometimes is very important in business and also in some economic type of application, right? The marginal effect of X toward Y is sometimes very, very important, right? Okay. So, and in order to do that, you cannot use machine learning model or artificial intelligence model, right? With that model, you actually do not have a marginal, cannot estimate the marginal effect like linear regression. So, although it's less precise, but because that you can, it is the only model that can estimate the marginal effect, which is very important in business and economic and some societal applications. Okay, so it's still very, very useful in most of in a large number of disciplines. You still need to use linear regression model to estimate to evaluate, to validate the relationship between X and Y, and also to estimate the marginal effect. Okay, so because it can, so it's less precise, but it's most useful. It's because that it's the only model that can estimate the marginal effect. Okay, let's say estimate the coefficient correctly is not an easy thing to do, right? Okay. In order to do that, usually you will need to learn a course. You will need to take the course called econometry. Okay, you heard that name, econometry. It's actually usually econometry is a 2-semester course. Okay, the textbook of econometry is usually like 1,500 pages, isn't it? Right? So, yes, it is useful, but in order to calculate the coefficient, it's very difficult to do that, because you need to check a lot of things, which I put it here, right? Correlation do not imply causality, the assumption of multilinear regression. You need to check a lot of things, and I don't have time to like cover it in our course, right? So if you want to have some better idea about how to estimate the coefficient correctly, here are two good reference, right? So you can see that there's introductory econometry. It's actually an online book, right? And it will tell you how to use R, how to use Python, or to learn econometry. As I told you that this kind of textbook used to have like 1,000 pages, right? So yes, the linear regression looks simple, right? But to estimate this coefficient correctly is quite difficult. But unfortunately, in our course, right? In our course, we do not care too much about the correctness of this coefficient, okay? Because we only want to predict the value of Y, right? In our case, in our case of our final presentation, in the Tafang case, the Y that we the reason that we build a model is to predict the probability of buying, right? For each of the customer, we want to predict that what is her probability of buying, right? And if her buy, what is the buying amount, right? So when we only care about the prediction value, then we don't need to worry about too much about the econometry type of things, right? Okay, so most of the actually I can say that 95% of the econometry textbook are talking about how to do the coefficient correctly, right? But since we in our course you only care about the prediction, so that complication can be set aside for now, right? Okay, but we must know that the complication is there, and it's actually quite difficult to do that. Okay, so this is my conclusion. It looks simple, but it's less precise, but it's useful if you can predict the coefficient. Okay, but to do that is not easy. Okay, so that is the conclusion that I would like to conclude today's course. Okay. Is there any question? Okay. If no question, then we were your assignment is to like trace the two notebook today and answer the question in HTML and upload it to the personal folder. Okay. Okay, so that's all for today. Next week we'll go to logistic regression. Okay. Okay. Thank you. That's all for today. Remember to turn off your desktop.